Ishai, and you better tell us talk about proofs and their applications.
Okay, thanks. Thanks, Yuval and Elaine for putting together this workshop. It's actually my first time here and in Pittsburgh, so it's great to be here. So I'll talk about dot product proofs and their applications. This is joint work with Neil, Palad, Ron, and David. And yeah, many of the slides, especially in the second part of the talk, are stolen from Ron, so thanks, Ron. And you know, the main themes of this talk are proof systems. By proof systems, I'm referring to PCP-like proof systems, information theoretic proof systems, cryptography, including computationally sound proof systems under cryptographic assumptions, and algorithms, specifically hardness and approximation. I'll spend a big chunk of this talk discussing some context and prior connections between them. And the main new object I'll talk about is a dot product proof, which is a new kind of a proof system. I'll tell you a little bit about constructions and mainly about applications, both in cryptography and hardness and approximation. Okay, so you know, we have a history of connections, you know, a lot of historical connections, both in terms of motivation and applications between these three main themes. And in fact, cryptographic applications and applications to hardness and approximation motivated different kinds of probabilistic proof systems. And this talk is also introducing a new kind of proof system, which is motivated both by cryptography and by hardness and approximation. And specifically, if you want to focus on two specific challenges in the two areas, in the area of hardness and approximation, the concrete challenge we address is obtaining exponential time hardness from the standard exponential time hypothesis. It says that you know, 3-SAT cannot be solved in better than 2 to the order of n time. And in cryptography, the question is how far can we push the succinctness, the communication of computationally sound proof systems. Okay, so these are the two challenges in the two areas that sort of motivate the new notion. So let me tell you a bit about existing connections, also making some detour into nice questions that might interest non-cryptographers. So in terms of applications between cryptography and hardness of approximation, there are quite a few, and we're seeing more and more of them. Let me mention a couple. So if you want you know, to derive the so-called gap ETH assumption, which is the exponential time hardness of approximating MAX-3-SAT, we can do it quite easily from assumptions about the existence of local pseudo-random generators, and this was strengthened by Applebaum to a smooth version, sort of an average case version of the standard ETH hypothesis, which follows from the existence of exponentially strong local one-way functions. So again, even though the final formulation for smooth ETH is more of an average case average case complexity assumption, both the results and the techniques were heavily inspired by cryptography and used cryptographic ideas. Another example is in the area of meta complexity. So if you look at the acronym of the paper, can you tell me who is not an author of the paper? It's not co-authored by Hirahara, so Hirahara co-authors, but this is what happens when you try to write a paper in meta complexity. This is by Juan, Gilango, and Ren, okay? So anyway, so they showed the hardness of versions of Kolmogorov complexity, time-bounded Kolmogorov complexity, based on witness encryption, and remarkably, they were also able to obtain some unconditional hardness of approximation results from cryptography. Now, this might look weird. How can you get unconditional results from cryptography? It turns out that there is also a different kind of cryptography, which is cryptography in a generic model. And results in this area are information theoretic. Think of it as replacing time bound by query bound, and then we can get unconditional results. So they use non-trivial results in cryptography, including both complexity-based crypto and unconditional results in generic models to derive hardness law approximation results for meta-complexity problems. Okay, and the primitive I highlighted here of witness encryption actually has several interesting connections with hardness law approximation. So let me tell you about, this is a detour about what I think is a very promising direction for applying hardness law approximation results in cryptography. So this is, at this point, a bit hypothetical, but I think it's within reach. Okay, so let me first tell you a bit about what witness encryption is. So witness encryption is considered a high-end crypto primitive. It allows you to encrypt the message M with respect to some NP statement X. So there's an underlying NP relation R. And the ciphertext C that you get can be decrypted by anyone who knows a witness W for the NP statement X. And if the statement is false, then M remains hidden. Okay, and you also have a stronger version which actually requires you to know the witness in order to decrypt. So the basic version does not, but morally it does. Okay, we can think of a stronger version where you can encrypt the message if and only if you know the witness that satisfies the NP relation with respect to the statement X. So if you want to see an example to illustrate it, I can take today, we can do it in principle. We can take the message to be, this is really an updated version of the Clay Institute prize. At the time, there was $1 million prize, no Bitcoins. Now we have $1 billion and not, we do have Bitcoins. So you can encrypt a lot of money in Bitcoin so that anyone who comes up with a proof that P is not equal to NP can collect the money automatically. You don't need to do anything, you just post it in public. And again, we can also make it extractable so that only people who come up with a proof will be able to collect the money. Okay, so this is an example to illustrate the notion, but it's really a high-end primitive. It does have a two-way connection with the goal of optimally succinct arguments. And so actually the connection is quite easy to explain. In one direction, let me just explain one direction of the connection. So if we have a witness encryption scheme, the verifier can just encrypt a random bit to the prover with respect to the statement that he wants to be proved. And then the prover sends back the bit and the verifier checks if it's the right bit. So we got a proof system where the prover sends just one bit to the verifier and the soundness error is roughly 1/2. And you can generalize this to S bits of soundness with S bit proof. So this is obviously, it's easy to see that this is optimal with respect to the prover to verifier communication. Okay, so this is, and there's also a connection in the other direction. Okay, so this kind of connects witness encryption to the theme of optimally succinct proof systems. How is it connected to the hardness law approximation? So first of all, just a bit of background about what we know. So we know how to build witness encryption. It's a pretty recent primitive. It's like 10 years old. Initially, it was constructed based on some kind of a fuzzy assumption about multilinear maps. It was later constructed from indistinguishability obfuscation, which thanks to the work of Ayush, Rachel, and Amit, can be based on well-studied assumptions. And sorry, I'm a bit, I didn't have much sleep, so sorry. And we know how to base it on the very strong and non-falsifiable versions of the learning with error assumption. This is due to Vinod, Daniel, and Otek. And we also have some heuristic constructions that we don't yet quite well understand. This is with Ayush and others. Okay, so the situation is that we cannot really, build witness encryption even heuristically from anything that does not rely on noisy linear algebra. Okay? And another downside of all of these constructions is that none of them is practical. Okay. So here's what I think is a really cool potential for big impact of hardness of approximation cryptography. And it's still hypothetical at this point, but there is a fair chance we get there. And maybe people here who study hardness of approximation can tell us how likely we are to be there. So the claim, I'll show you how we prove. This is the joint work with Bartosz Ostrowski and with David Wu, who's here, is that if we get what seems to be a small step in the hardness of approximation of a specific problem, namely the hardness of approximating the minimal distance of the linear code, this would lead to solving the witness encryption problem for general NP languages in the so-called generic group model. You can think of it as a discrete log style assumption. Okay, so because the result is still hypothetical, we haven't even bothered formulating like a nice concrete assumption. But this is the common generic model, the generic group model. Many practical schemes are analyzing this model. We get, based on a hypothetical but seemingly modest improvement in the state of the art, we get this big result on witness encryption. Why is this big? Okay, so let me tell you soon why this is big. But let me just say that the conclusion here is to take a very standard generic model, non-noisy linear algebra, and in this model, assuming we have this hardness of approximation result, we get an unconditional construction of witness encryption. Okay, so a bit about what we need, what progress we need in hardness of approximation. So again, the concrete problem is that you're given a linear code, say by a generating matrix, and you need to approximate the minimal distance of the code, or equivalently the weight, the Hamming weight of the lightest vector code word in the code. What we know for quite a while is how to, this is an NP hardness result. It's actually constructive NP hardness result for any constant factor approximation, which works over any polynomial size field. Okay, you can get below, you can get above constant factor, but this would require the reduction to be super polynomial, quasi-polynomial. We need a reduction that establishes NP hardness to be polynomial time. And in this regime, we have hardness of approximation for any constant factor over any poly-size field.
I'm not sure.
Yeah.
So are you sure we know it for polynomial size fields? I feel like.
So it's a simple generalization of existing results.
No, but the way it works is like really complex, and I think field size I feel like probably would be exponential even the reduction last. Is it true?
You might be right. David, do you remember?
I think the lot and this is like 4 years old. Right. I think it's not
Okay, and in any case, what we need is the progress in the two dimensions. We need the approximation factor to be super logarithmic, and we need the field size to be super polynomial. But any super log and any super poly will work here.
So you got again, the way you amplify approximation is the tensor. That'll blow up the dimension.
This blows up the reduction time. So you can get to the square root log n, but this will
but you're happy with blowing up the size of the field, but not. So you want to.
Yeah, we want, again, so current techniques cannot achieve it, but at least, according to Subash at the time, he did not see any apparent barriers. I don't know, Ryan, do you have any intuition? No is a good answer in this case. But one thing to note is that by hardness here, we really mean a constructive NP hardness. Intractability is not good enough because we have solid evidence that the problem is intractable even over super polyfields and even with very big factors. What is this solid evidence? Can somebody guess? No. If we live in the LPN assumption over big fields, then this implies this result. But we actually need, because the witness encryption is actually constructive, we need the reduction to be constructive. So there's a difference between assuming something is intractable versus assuming there's a reduction. Okay. This is also why we cannot get a heuristic construction just based on the hypothesis that this is true.
One technical point is like, my recollection of when I was looking at these reductions was that many of them don't preserve witness map to witness, which
Right,
is what is required.
Yeah, but the standard ones do. So you can map.
Yes.
Yeah, but this is indeed needed here. So we need an NP hardness in a sense that you can map a witness to a lightweight vector code word. Okay, and again, why is the conclusion? So this is basically why the assumption looks plausible. Why is the conclusion interesting? Again, it's 20th century style. So the first proposal for public key encryption was based on a discrete log style assumption. This is also, again, a discrete log style assumption. It's unconditionally true in the generic group. You model the group as the generic oracle. This also means that we only make a black box use of a very basic crypto structure. And these things make this construction potentially practical. So to conclude, if there is progress on this kind of mainstream problem in hardness of approximation, it might have a very big impact in crypto. Okay, and again, this is the tip of an iceberg. If we have witness encryption in the generic growth model, we'll probably have many other applications. So basically, we have a pretty big impact on crypto. So people who work on hardness of approximation, please work on this problem.
This people convince
Again, if you're okay with the generic bilinear setting,
yeah,
does that make the thing on the left sort of easier? So
good question. We did not see. I think we saw that in this direction. We did not see how to do it. Again, we're likely to be missing a simple trick, but we tried to find it and failed. Yeah, it seems really we're frustratingly close to getting something very interesting. For now, it's only hypothetically interesting.
Just to try to understand, right? So the way you get witness encryption for NP is you will do the reduction.
Yeah, I will show exactly. Yeah, I will show this result again. It's only this is really the detour part of the talk, which might be a later part. But I think it's a good fit. It's a good fit for this workshop. Much better fit than the topic main topic of the talk.
That's exactly the point.
Yeah. But how much time do we have? Okay, good. Cool. So let me explain this construction. And in fact, you can really think of it as a slight variation of the classical but not sufficiently known public key encryption scheme due to Alekhnovich. Okay, so Alekhnovich, by the way, concurrently to Regev, he figured out how to build public key encryption from the learning party with noise. The bind, even it works over any field, and I'll tell you about it. It's quite more general than that, but let's think of the standard LPN problem, which basically means that if you pick a random linear code and you give me a random code word with a random low weight noise, so a random code word plus a random sparse vector, I cannot distinguish the two from random. Okay, this is the LPN, and what it also implies is that we can plant a random sparse vector, and we denote it by E1, in a random linear space V. So here V actually denotes a random linear space conditioned on containing a random sparse vector E1, which by the LPN assumption is indistinguishable from a totally random linear space V, which most likely will not contain a sparse vector. Okay, and this is the public key. And the secret key is a sparse vector E1 that we planted inside V. Okay, now how do we encrypt and how do we decrypt? So encryption works in the following way. If you want to encrypt the bit 0, you just take totally random vector, okay, most likely outside the code. If the bit you want to encrypt is 1, you take a random vector V in the dual space. So a random V is subject to being orthogonal to all vectors in V, right? This can be easily done based on the public key alone. And you add an independent random sparse vector E2. Okay, and the sparsity should be chosen such that if you take the inner product of E1 and E2, it will be biased towards 0, so less than square root n Hamming weight. And now for the decryption, we use the secret key E1. This is the planted vector here. We just take the inner product of E1 with the ciphertext. In the random case, we obviously get, in the 0 case, we obviously get the random bit because, you know, any non-zero inner product with random is a random bit. In the 1 case, we will actually, this dual vector will cancel out because it's dual to everything, including E1. And then we will just get the inner product of the two noise vectors, which will be biased towards 0. Okay, so it's very cool. It could have been even very practical if it weren't for this limitation of square root and noise, which, by the way, you can try to think of generalizing the noise distribution. It turns out it actually follows from recent results in additive combinatorics that you cannot generalize this in a way that will pack more entropy into the noise vectors. Okay, so we're kind of stuck with this square root n for constant size fields. If you allow the field size to be super constant, you can easily come up with two noise vectors whose inner product is biased by just taking them to have low L2 norms, and this is basically Regel, or dual version of Regel. Okay, so if we want to construct witness encryption scheme in the generic group model, we just put Alekhnovich in the exponent. That's basically it. We also need to move, this can work over any field, including the binary field. Here we need the field to be big because we need the inner product not only to be biased, but also unpredictable.
This is why the large field.
This is why we need the large field. We need the field size to be super polynomial. And the scheme is syntactically the same, except that you put everything in the exponent of a cryptographically hard group. Okay, so 0 is G to the R. This just means a vector of n random and independent group elements, right? When I write generator to the power of vector, I mean raise the generator to each entry. The 1 is encrypted as G to the power of the ciphertext of 1 in Alekhnovich encryption. And then the decryption is also done in the exponent. And the syntactic difference from Alekhnovich, except for increasing the field, is that now the linear code, there is no public key, right? The linear code is really the instance that is generated by the reduction, right? That establishes the hardness of minimal distance. So for yes instances, we know, right? This is a feature of the reduction, that we can map our NP witness to a low weight vector, okay? And in no instances, this linear code, right, which is generated again efficiently from the instance, will not have any light vector. So there will be a gap which is super logarithmic between the weights in the yes case and the no case. And again, if we choose the weight of E2 such that in the yes case, we will get 0 with high probability, and in the no case, we will get 0 with negligible probability, right? So we need the Hamming weight of E2 to be roughly n divided by the Hamming weight of E1, which is really, again, the reduction. There is a gap between yes instances and no instances, so this is the Hamming weight of yes instances. Then we're in a situation that you really have, so let me explain why this is secure. So it's easy to see that if you have a witness, then you know E1 that has sufficiently low weight so that the inner product of E1 and E2 will be 0 with high probability. Okay, just because the product of the two is less than n, the product of the two weights. Okay, so then you can distinguish because this will be biased towards G to the 0, towards 1. If you're in a no instance, then there is no vector in this space that has sufficiently low weight. And then your only strategy of distinguishing, you can only basically take inner products. In the generic group model, this is probably the case. You can only take inner products with the vector that's encoded in the exponent, and then you can prove that you need a super polynomial number of queries to distinguish. Okay, your only bet to cancel this component, you need to take a vector in V, and if it has it must have, in the no case, high weight, which will make this.
So
yeah.
And you're taking inner product with a random, somewhat high weight vector, and it's
Exactly. Yes.
And the omega log n has to do with the exact security. Like if it's only log squared n, you only get like
Yes. Exactly. But again, we believe, again, we know it's only about the question between intractable versus NP hard. In terms of intractability, we know the answer. And
people again, where does the omega log n come from? If you just want half security,
it's about the probability that the inner product of E1 and E2 will be 0.
So Yuval, for the other problem, NCP, the nearest code word, a fine version of MVP.
Yeah.
The problem is completely sorted, right? We have it over
Yeah. For the MCP, we can get much less interesting results. So we still have some applications to succinct proof systems, but we cannot get, if you look at the affine version of the problem, like the closest vector instead of shortest vector, then, it's not enough for all we know for witness encryption. Okay, so now let me briefly, again, still before talking about the actual results, let me give you a quick context about proof systems. So again, we all know classical PCPs, this is how a reviewer should read a paper. This is how a reviewer actually reads a paper. And a PCP makes this like this. And there is the crown jewel of theoretical computer science in general, which says that every classical proof could be efficiently encoded in this way. And this had a huge impact both in hardness of approximation results and succinct arguments. If you want to apply PCPs in the wild, you cannot just have the prover communicate the PCP. It's too long. You cannot have the verifier send the queries to the prover because this breaks soundness. So we need some kind of a crypto compiler. The classical compiler suggested by Kilian and Mikali says to the prover, first succinctly commit to the proof using a Merkle tree, a tree of hash functions where the proof bits are in the leaves of this tree. And then the verifier asks the prover to locally open the commitment. So let's say the verifier wants to read the fourth bit of the proof. Then the prover reveals the hash values along the path, along with their siblings. And this is how it works, right? This is how you take PCP, a classical PCP, and convert it into a succinct argument. And this works in theory, but if you think about it, it's a highly redundant process. Okay, we take the witness, we apply this huge machinery of the PCP encoding, complex both in terms of understanding and implementing, and then you hash it down. So it seems redundant. It sounds like there should be some kind of a shortcut. Okay, this part is computationally heavy. And also in terms of the level of succinctness, it leaves much to be desired because you have two sources of overhead. First, if you want to get good soundness in PCPs, you must make many queries. Okay, so this is one source of overhead. And second, opening this tree of commitments has a logarithmic overhead in the runtime. So these two sources of overhead are meaningful in theory and have also significance in practice. And to this end, the crypto community came up with two relaxed versions, two orthogonal relaxations of the PCP model. The first adds interactions, so the prover has multiple rounds of proof, where between two rounds of proof there is a random public challenge. Okay, so there is an initial proof generated by the prover, then there's a random challenge and a second proof and so on, and then the verifier makes queries to all of these proofs. So it's sort of combining interactive proofs and PCPs. This was first suggested by Kalai et al., who first realized that this combination is powerful and later generalized in what is known as interactive oracle proofs, which is now a very mainstream object. And it's useful. There are a lot of nice theory results. You can compile such IOPs using essentially the same compiler, and it led to many practical systems. We just had one of the best paper results. We'll hear the second in Vinodstock, but one of the best paper results in the last crypto was really yet another improvement to these IOPs that has practical significance. The second relaxation, which is relevant to this talk, is to just sort of change the query, the power of the queries. Okay? Or another way of thinking about it is thinking of the PCP as a function from a restricted class. So now in this linear PCP model, and again, this was motivated by the fact that we wanted to get succinct arguments without using the PCP theorem. So here in this relaxed model of linear PCP, we consider the proof to be a vector over a finite field F. And now the verifier can make these inner product queries. Each query of the verifier can take the inner product of the proof pi with some vector qi selected by the verifier. Okay, so you can think of the proof as being a linear function that is queried by the verifier. Okay, and now the verifier gets the three field elements, which are the results of these inner product queries, and together with the input and the queries, and decides whether to accept or reject. Okay, so this is the linear PCP model. We can also compile them into succinct arguments using different kinds of homomorphic encryption-like primitives. Sometimes it's pairing, sometimes discrete log, sometimes actual homomorphic encryption. And this has also led to practical systems which tend to be more computationally expensive, but also more succinct than the IOP-based proofs.
You charge unit cost per query, right? Even though the query is potentially big.
Yeah, I mean, you count the number of queries. Right. Yeah, you can have, roughly speaking, in these crypto compilers, the number of queries corresponds to number of ciphertext or group elements in the proof. And the final extension of the linear PCP model, or restriction, if you like, is called the fully linear PCP, which was introduced, in work with Bonnet-Boyle, Henry, who's here, and Gilboa. And this is motivated by cases where the input statement, which is normally in the hands of the verifier, is actually distributed in some way, or encrypted or committed. Okay, so in some cases, the verifier does not really have direct access to the input, but it can still manipulate it using a linear function. Okay, in all these cases, secret sharing, encryption, commitments, we can cheaply compute linear functions of the inputs and not more complex functions of the input. And the fully linear PCP is just like a linear PCP, except that each query applies jointly to the input and the proof vector. Okay, so it's an inner product of the concatenation of the input and the proof vector with some query vector. And note that once we make this restriction, then similarly to PCPs of proximity, this notion becomes meaningful even with unbounded prover and verifier, even for finite languages and so on. Now it becomes a purely information theoretic notion. And in fact, most known constructions of linear PCPs can be made fully linear without even increasing the query complexity. Okay, so briefly, just to pitch some features of linear proof systems that do not exist in the other in the PCP-like models. First of all, they can be extremely simple. So this is implicit. If you ever teach PCPs, you teach this Hadamard-based PCP, which is the easy component in the ALMSS result, and here we make it easier by even eliminating the linearity testing part, which is the heavy part in this Hadamard PCP. We don't need linearity testing because the malicious prover is bound to using a linear function. So really the proof is just take the extended witness, right? The values of all wires in the circuit you want to satisfy, and tensor it. This is the proof. Literally, this is how the PCP looks like. Right, so this is quadratic size, and you know, subsequent research shown how to make the size linear in the circuit size for circuit SAT. We can get soundness error that scales inversely with the field size, and you can think of the field as being super polynomial. This means that we can get negligible soundness error with just a constant number of queries, which we cannot get in the classical model or in IOP model. Soundness can be reusable, which means that there is essentially no correlation between the event that the verifier rejects and the proof, even for badly formed proofs. This has applications to reusing the same queries for many proofs. And in fact, we can even have just one query linear PCPs by compiling any classical PCP, but this comes at the cost of losing all of the above advantages, right? So if you look at this compilation result from prior work with Vitansky et al., it really loses linear size because we don't know of any linear size PCPs. It has bad soundness. It's not reusable in an inherent way. Okay, so we basically lose all of these advantages, and this is the motivation for the work. So finally, I get to the notion. How much time do you have? Okay. Excellent. So I'll take 1 minute just to tell you the gist of what we show.
I'll see constant number of minutes.
No, that's fine. I want to wrap up. So really what we do in this work is we take simplicity to an extreme. We look at the one query fully linear PCP. So I basically already told you the definition. And the main, so I will just tell you the two main results. So we give an optimal construction over constant size fields. So again, you take a single inner product between input and proof and query, and you get soundness error, which is inverse in the square root of the field size, which we showed to be optimal. And this result has a direct application, right, along the standard lines to the hardness of MAX-LIN. So we give, this is an elementary construction. We get both an elementary hardness result for MAX-LIN, maximizing the number of satisfiable linear equations in a linear system. And it has the feature, because the proof size is linear in this case, it has the feature that under the standard ETH assumption, we get exponential time hardness. Okay, so this is really uncommon. I think there's only a very recent result of Guruswamy et al. That shows under standard ETH a natural hardness, natural non-trivial hardness of approximation, exponential time hardness of approximation. And this is again optimal. And the second result is really showing that the caveat of the first result is that there is an overhead in the proof length, which is polynomial in the field size. So this also limits our level of soundness. If we want to get negligible soundness error, then we cannot use the first result. We have a second construction which works over big fields. Here we are much more loss in the parameters. So you can get any soundness error over field size, which is polynomial, quite a big polynomial in the size of the circuit, the circuit size instance and the inverse soundness error. So the bottom line is that you can still use it. It does have cryptographic applications to succinct arguments, so very efficient succinct arguments of some kind. But at this point, it still needs, there is a big polynomial gap between the soundness error we achieve and the one we can hope to achieve, and closing this gap can have significance for applications. Okay, so I'll conclude with just mentioning, I think they're really nice. We nailed down some of the questions, but I think really, bear with me for one more minute. These are questions that are mostly, in the PCP territory. So if you look at one query, forget about DPP. For DPP, I said we can only get 1 over square root field size soundness. Here Q is the field size. For one query linear PCP, we can take the optimal hardness of approximation results for MAX-LIN and convert them into one query linear PCP with near optimal soundness, 1 over field size. We don't know whether this can be done with perfect completeness. We don't know whether this can be done while avoiding the PCP theorem. And we don't know, we feel like there should be some slight extension of DPP that allows to go beyond the 1 over square root field size and go to 1 over field size soundness. Okay, so yes, with that, and sorry for running out of time and so on. Thanks.